Alright, this is our second video. We're going to talk about sound a little bit more, do a little more with some of the calculations with it. So first off, volume, how loud something is. In the first video you might have heard some pots and pans and my wife crashed in the background. How loud is that? How do we know that? And you probably have heard some terms like decibels. But what's interesting is that decibels is more subjective than you might think. You know, if I consider a sound loud because I'm old, some of you youngsters might not think it's so loud. So how loud a sound is a very subjective thing. So that's something that physicists have to contend with. So what they do is instead we think about the sound intensity. How intense is that sound? That's something we can measure. So first off, we can take a look, got a formula here. Let me pull up a highlighter. We got a formula right here. And this is a very important formula. This is how we calculate the intensity. Now notice that I is different than the I we used in the last unit for electrical current. Even electrical current, you know, the amps, that was how intense the electricity was. So once again, we're using an I for intensity. And it's calculated by power divided by surface area. Now, the way we model sound is we think of sound as a giant circle. So we got our source of sound, and as the sound waves travel outwards, we think of them as traveling out spherically. Well, the surface area of a sphere is 4 pi r squared. So the way we calculate the intensity is we take power, which is measured in watts, divided by surface area, which is measured in meters squared. And notice that sound is going to obey the inverse square law. So if I double my distance, I got 1/4 the intensity. If I triple my distance, I've got 1/9, 1/16, 1/25, so on and so forth. So sound obeys an inverse square law. When it comes to measuring this, you know, it kind of goes with the amplitude. So the larger the amplitude, the louder the sound is, at least the louder the intensity is. So there are a couple numbers here that we need to point out. There are two thresholds, the threshold of hearing and the threshold of pain. So the threshold of hearing, this is the quietest intensity that the average human can hear. And that is 1 × 10⁻12 watts per square meter. Sometimes we use the symbol I with a sub naught beside it. Then we have the threshold of pain. This is where the average human would experience physical pain because of something being so loud, and that's actually 1 watt per square meter. So, just as frequency determines pitch, intensity determines loudness or the volume. Volume, though, is not directly proportional to intensity. It's approximately logarithmic in our ears. So when we go to calculate how loud something is, we typically use a relative intensity, and that's what the decibel level is. Decibels are the relative volume of a sound. It's a logarithmic unit, and it's always related back to the threshold of hearing. So the formula for it, you can see, it's not too bad. It's 10 times log, and in the argument of the log, we've got the intensity divided by the threshold of hearing. What this kind of means, because of this log, remember log is base 10. If it's, you know, not told, if you're not told what it is, it's base 10. So a difference in 10 decibels means that the sound is approximately twice as loud. So 30 decibels is about twice as loud as 20 decibels. So when I go from the threshold of hearing to threshold of pain, the threshold of pain is about 4,096 times louder than the threshold of hearing. And here is a chart with, it's kind of handy here, we got threshold of hearing all the way down here, and we see that its decibel level is 0. That kind of makes sense there. And then if I have something like a normal conversation, that's 1 times 10 to the negative 6. That works out to be 60 decibels. So 60 decibels, that's about conversation. When we get to some threshold of pain, it's not on this chart, but it actually works out to about 120. So about 120 decibels, that's at the threshold of pain. We get some extreme pain, a jet airplane. Now, I've looked this up before. There's some kind of disagreements, but the loudest a sound can be is about 190 decibels. Remember that sound is a mechanical wave. It's a longitudinal wave. So what happens is the louder something is, the greater the amplitude. And for that, a larger amplitude, that really kind of means a thicker compression and a smaller rarefaction. So at 190 decibels, that compression part of the longitudinal wave is so thick that it runs into the next compression, and the sound wave kind of jams up on itself. And that happens at around 190 decibels. So the loudest any sound can be on Earth, with our nitrogen-rich atmosphere, all the other conditions, it's around 190 decibels. Okay. Now, for some other kind of fun things with sound here. So a forced vibration. This occurs when energy from one oscillating system is transferred to another. And that happens through sympathetic vibrations. And this is where I wish I was in my classroom to really do this for you. Do yourselves a favor and go to YouTube and just type in watch some videos on this. Get some demonstrations going. I've got these special tuning forks mounted to boxes, and I'll strike one, put my hand on it, muting it, and the other one will still be playing the same sound. And that's because the sound waves from the first box traveled through the air and excited the second box. Sometimes I'll do this also in the music room. If you play a note, the greatest instrument of all, the saxophone, if you play a note on the saxophone, while someone's holding down the resonator pedal on a piano, the piano will begin to play that same note. And there's a couple ways that this kind of works here. First off, we have to know something about natural frequency. If you were just to strike something, everything has a different natural frequency if you kind of strike it. If someone drops a wrench versus dropping a baseball bat, you would be able to tell the difference between the two. They have different natural frequencies. So if you play a note and you have a string in the piano which has its own natural frequency, if you play the same note, the same frequency, the same pitch as the natural frequency, well, that string will begin to sympathetically vibrate because it is resonating at that same frequency. So what resonance is, it's a condition. It exists when the frequency of some forced vibration applied to a system matches the natural frequency of that system. So another example is someone runs their finger around the rim of a wine glass, causing it to sound. That's a resonance. When an object can resonate, it is vibrating at its natural frequency. So if it continues to receive that energy, the amplitude increases, and it could potentially cause something to explode. So again, go on YouTube. You can find these examples all over the place. Great example. Now, I know the myth is that there's an opera singer who can do this with their voice. I just don't see it happening. The demonstrations I've seen in college, you had to have a very powerful loudspeaker. They put a tuning fork in there with a microphone. They kind of tap it a couple times. A computer records the natural frequency of the glass, and then it plays back that frequency through the loudspeaker, and it gets very loud. I just don't see the human voice causing this, but I've been wrong before. But, opera singer breaking the wine glass, that's the classic example of resonance. Try to find it if you can. Might be kind of a fun video to watch. All right, Doppler effect is the next topic here. So this is when the observed frequency of a wave depends on the relative motion of the source. And on the AP exam, we're just going to do a qualitative treatment. We're not going to do any math with this. Now, this all comes back to the speed equation. V equals frequency times the wavelength times the frequency. Now, if I've got something moving, it's moving through the air. Well, I'm not changing the temperature of the air. I'm not changing the air into hydrogen. I'm not changing the air into steel. The speed is going to be constant. The speed of the sound waves, that is. So when this object is moving, notice how the sound waves kind of get bunched up in front of it. This causes the wavelengths to get shorter. And since I'm not changing the speed of the sound, that causes the frequency to go up. So if I take a look at my formula here, as the wavelength, if I can draw this out here, goes down, the frequency must go up. So on this end, I'm going to see a higher, or observe a higher frequency. Now I've had students in the past try to tell me this. They'll try to tell me that the Doppler effect means that as a source of sound approaches you, it gets louder. Duh. Yes, of course it's going to get louder. Doppler effect is not about volume. It's about frequency, and we perceive frequency as pitch, high versus low notes. So as a source of sound, like an ambulance, approaches you, you'll hear the frequency, the pitch, rise. And as it recedes, as it goes away from you, the wavelengths are going to be stretched out. Well, longer wavelengths mean a lower frequency. So as a wavelength gets bigger, the frequency must get smaller. So again, the Doppler effect, please, please, please do not be one of those people who says, the Doppler effect means that as something gets closer to you, it gets louder. Don't be that person. No. The Doppler effect means that as something approaches you, as a source of sound approaches you, its frequency increases, and as its wavelength gets shorter. And once it passes you, the wavelengths get stretched out, and the frequency drops. It gets lower. Now, this Doppler, here's the equation for the Doppler effect. Again, you don't need this for the AP exam. I just throw this on here in case you have to make the calculation in college. Honestly, it's not hard. I promise you, it's not hard at all. There's a couple things you got to keep in mind with pluses and minuses, but it's honestly not difficult, so we're not going to worry about it. Now, the Doppler effect, I've been talking about it in terms of sound. The truth is, the Doppler effect is true for all waves: water waves, sound waves, and light waves. Now, as a star, a source of light, approaches you, the wavelengths get smaller, and that causes the frequency of light to increase, and that shifts it towards the blue end of the spectrum. And as a star moves away, the wavelengths get stretched out, and that causes the frequency to be shifted to the red end of the spectrum. We call that a redshift. And in astronomy, when we look out in the sky, when we look at galaxies, observing the Doppler effects, we see a predominant redshift in the universe, meaning that our universe is expanding. Everything's moving away from us and we got the Doppler effect to help prove that. All right, this next page is not in your notes. Don't worry about that. Okay, I think we're going to call that video 2, because video 3 I want to take my time with that. So, couple things to remember. Doppler effect is not about volume. It is about frequency or pitch. Again, I cannot say that enough. I've had AP students in the past do that, and I've laughed at them. Don't be a person I need to laugh at. All right. Talk to you later.